Hey, this is an introduction to chemical equilibrium. It's really about the reversibility of a chemical reaction. Consider, for example, A plus B turning into C plus D. Isn't it possible that C and D can react to form A plus B? Oftentimes they do, and things won't come to an equilibrium until the rate of that forward reaction is the same as the rate of the reverse reaction. That's the point at which you have equilibrium, and note that that's not the point at which the reaction has stopped. Things are still occurring, it's just at equal and opposite rates. Sort of like you're running on a treadmill. And we can define the rate as being equal to some constant K times the concentration of A raised to some power times the concentration of B raised to some power, where those exponents are determined experimentally. They might be first order, second order, with respect to each reaction. We call that rate law. That's different from chemical equilibrium, which can be calculated. We define it using the concentration of the products over the reactants, where the coefficients, in stark contrast to reaction rate, are used as exponents in the equilibrium constant expression. What are these K's all about? I just think of it as if this is a low number, the reaction is relatively slow. If this is a low number, the equilibrium is fairly, shall we say, low also. You have a lot of reactant forming backwards every time you go forward to make product. This is the equilibrium constant. And yeah, low number might be bad, you're just not getting anywhere. Big number might be good. There's not a whole lot of reversing going on. We need to only consider those things that can reverse. Once something pops out of solution or leaves the reaction mixture, whether it be solid, liquid, or gas, you are out of equilibrium. So as a general rule, watch out for liquids and solids. We omit them. They cannot reverse. Now, in reality, your equilibrium constant is what should happen in theory. But before you get there, you might be at a lower or higher value than that equilibrium constant. Imagine things have just, not gotten rolling very long and your Q is less than K. Well, that must mean Q, by the way, is the actual ratio of the products to reactants that's measured at any point in time, not necessarily at equilibrium. If it's too low, well, the reaction still has a ways to go. It will proceed forward. It can be that somehow it got beyond that. You have much more product than you have any right to occur when you're in equilibrium conditions. The reaction will naturally reverse itself to going to the left, that's backwards, until it matches that equilibrium concentration. That's a comparison of what they say Q versus K. Okay, let's have a look at a couple scenarios. Oh, we've got hydrogen and iodine reacting to form hydriodic acid. Let's write down the rate equation. Well, it's simply the concentration of the products, which is hydriodic acid. There's our coefficient becoming an exponent, divided by the two reactants. And we can include them all because everything's in equilibrium. Everything is in the solution. It's in the gaseous phase. For this one, not so much. We've got a solid here and a solid there. We're going to omit them. They cannot reverse, and therefore they are just locked in. So it's going to be equal to the concentration of carbon dioxide over the concentration of carbon monoxide, and that's it. Here's one where we have some data and we'll have to solve it. Oh, look at this. They actually give you KEQ. I'm guessing that they're going to give you 2 of the 3 product and reactant concentrations, and you calculate the other one. And there's one of the products. There's the starting material, and we need to find out H2. Yes, everything's in equilibrium. We'll set up the expression. There it is, and it's given, the equilibrium constant, and everything's given except hydrogen. So let's plug in. So we just need to solve for that number, and then we'll have it. When you do the math, you'll find out that the hydrogen concentration at equilibrium is 0.0377 moles per liter. This is an introduction to chemical equilibrium.